Thank you so much. So this is a this is the first lecture. The next one will of course be next week, right? In this lecture, I want to start with some general machine learning concepts and also with some general ways of introducing and integrating persistent homology and topological data analysis in general into these type of models. So the first part of this two-part lecture is entitled features and kernels, because that's what we will be dealing with. And I assume that you've all been briefed on how TDA works and how persistent homology works. I'm not going to be able to give you a full understanding, of course, of the vast field of machine learning, but I'm going to try, and I'm going to try to give you an idea and an intuition behind the most relevant facets. And I, of course, hope to do this in a lightweight manner that makes it appealing to everyone. So if we start, this is one of my favorite cartoons about machine learning. This is how I explain machine learning to my parents, for instance. So it's basically all linear algebra. You pour data into linear algebra, and then you collect the answers on the other side. And if the answers are wrong, then you just stir the pile until they start looking right. And this whimsical cartoon has a true core in a certain sense, because indeed many of the concepts that we are dealing with in machine learning research are based on having data and some kind of linear algebra with some kind of way of steering the pile, which means training the model. Now, what makes deep learning actually special in this case? And this is don't take this cartoon too seriously, because I don't think there's a big dichotomy between, let's say, shallow learning or classical machine learning and deep learning. But one thing that makes deep learning special is that it is very much like a Lego brick type of construction. So whereas in classical statistical learning, you think a lot about empirical risk minimization, for instance, or things like the intrinsic dimension or the VC dimension of your data. In neural networks, at least that's what some people have the expression of, is you just stack more layers, right? You just put more stuff in your architecture, in your model, or you put more data into that. That's of course not the whole truth. But one thing that is true about deep learning is that it uses task-specific features. That's the new thing. And this is something that I want to underscore by the idea of what a neural network actually is. So one perspective that I like to have for general neural networks is to say that it is a way to, well, as I said, build something with Lego bricks. So you can reconfigure it in different ways, and you can use it to create different types of architectures, different types of task-specific models. And this is really key here. So in contrast to earlier classical machine learning techniques like a support vector machine or a random forest, the idea of a neural network is also that it somehow incorporates features from the data, features that are relevant for a specific task. We will come back to this aspect many times over the course of this lecture and the subsequent one. So I'm just going to let this stand. The more mathematical perspective that I actually also find very relevant and very helpful when thinking about neural networks is to think about them as universal function approximators. And the specifics of this theorem here, which is one of many universal function approximation theorems, they are not super relevant, but the overall shape of all these theorems looks as follows. It says that given some kind of neural network, which is typically done by having a kind of linear algebra equation ax plus b, right, followed by some nonlinear function sigma, given this type of neural network, it is possible to approximate any type of function coming from a specific type of class of function, maybe. So in this case, it has to be compact and continuous and so on and so forth. But it is possible to approximate any type of function to arbitrary precision in a way. This is expressed by this idea of saying that the supremum of the distance between the values is less than epsilon. And this is a very helpful perspective for dealing with neural networks, because it means that even if you have a very, very complex function underlying your data, it is, in theory at least, possible to do this approximation. Now, it's a theorem, right? So there are differences between theory and practice. These theorems do not necessarily guarantee that you will end up being able to approximate your function up until that specific resolution or that specific error, but it at least tells you that there exists a specific architecture or a specific set of weights that make this work. So both of these perspectives, the Lego bricks and the universal function approximation perspective, are very, very helpful for me personally to understand and make sense of this. Now, we move a little bit further. A lot of the things that I will be talking about tonight, today, wherever you are in your time zone, is following the moniker of representation learning. So representation learning is a subfield of machine learning, and the slogan of representation learning is, very abstractly said, we map things into vectors in some high-dimensional vector space, and we use that to do that. We use maps that are often, but not always, learnable and thus, in a sense, task-specific. So that's the goal. That's the slogan of this whole field of research. And you might have already heard of some, let's say, very famous representation learning techniques. For instance, there's the famous word-to-vec representation learning algorithm, which essentially can take text and give you nice embeddings from that. So look at the date of this preprint, right? That is from 2013. This is not a typo. So this predates large language models by more than a decade, right? Which is not to say that word2vec has solved all the problems in natural language processing, of course, in natural language programming, but it goes to show that there is already a wealth of research and representation learning that is not necessarily making use of deep learning. But of course, deep learning always comes into play sooner or later. For instance, there's a Node2vec approximation of this. This is a 2016 publication, which is used to embed graphs, or more specifically nodes of graphs, into high dimensional vector spaces. And then very recent work in mathematical terms is work by my colleague and friend Celia Hacker. It's called K-simplex2vec. It's a simplicial extension of Node2vec. And then so you can see that the slogan of saying that we map things into vectors is indeed true, because the things can be either words or texts, they can be graphs or networks, or they can even be simplicial complexes. And of course, the list could go on and on. So, I mean, this is by no means a complete list. My colleague Mustafa has work on combinatorial complexes and CW complexes and how to embed those and how to solve learning tasks from those. I'm mentioning those here because they form kind of a basis of what one can do in this realm. Now, what will we do in this lecture? In this lecture, we will be talking mostly about the landscape of topological descriptors. So you have heard a great many lectures that are much more comprehensive in terms of the topology than this lecture here. And so I'm just going to start where those lectures ended, and I'm going to discuss how to deal with the topological descriptors that we have available. So what choices of topological descriptors do we have? What are their properties, advantages, and disadvantages respectively, and how to integrate them into a learning process. So that's the goal for the next next half hour or so. All right. Of course, the first descriptor you already know. This is just your venerable persistence diagram, and I should say I may be a little bit vague or imprecise in my thinking here, but for me, persistence diagrams and persistence barcodes are really more or less like the same thing. I like to draw them as a diagram because it looks a little bit nicer, but you can really think of the same thing here. Now, the points in a persistence diagram are, of course, tuples in R times R extended, so you can have infinite tuples. We're not going to discuss what happens with those. We're just going to assume that we have those. The persistence of every one of these tuples, of course, corresponds to the distance to the diagonal. But if you look at this, the multiplicity of each point is typically not apparent from this diagram. And in some sense, if you visualize it, the space under the diagonal is typically not used for anything, right? Moreover, it has a type of set structure. So this is just a set of points, which means that it's very, very hard to address or solve any type of learning task from this, because if I give you 5 persistence diagrams, they might have different number of points, and in fact, generally speaking, they will have different numbers of points, and so it's quite hard to learn something with this. But we can do something with that, right? So I'm just recapitulating a couple of things that you will have seen already, of course. So we can calculate distances between persistence diagrams. So for instance, we can calculate the bottleneck distance between those diagrams, which involves solving an optimal transport problem. So we find the best bijection between the point sets, and we do this using the L-infinity distance. Or we can extend this distance to the Wasserstein distance. Instead of solving this supremum here, we can also solve an infimum over all these costs and weigh that appropriately. What can we do with those? Well, if we have distances, a very simple way of dealing with different persistence diagrams in a data set would be to take the pairwise distance matrix and use that distance matrix as an input to a neural network, for instance. But before we get there, I want to show a couple of advantages or a couple of properties of these diagrams, just to get everyone on the same page, because that will be relevant later on. So first of all, the differences between the two distances can be seen if we look at the actual optimal matching that is being calculated. In the bottleneck distance, on the left-hand side, this matching is basically determined by a single match, namely the bottleneck that you have to squeeze your data through, as it were. In the calculation of the Wasserstein distance, by contrast, all the other points are involved somehow, and the rest is of course matched to the diagonal. So that is kind of a very important distinction, because it means for the calculation later on, it means that in terms of the bottleneck distance, you're using different types of features, different parts of your data for the actual calculation. Now, in practice, we can do this, right? We need to solve some optimal transport problem. There are fast algorithms for this purpose, although of course it's still not the fastest that you can do. It's not linear, for instance, and there are approximations, for instance, by my colleague Dimitri Morozov and others, of course. So we can approximate those distances, but in general, the scalability might not be too good. But, and this is where we now make the switch to other measures, the key insight. And here I'm going to slow down a little bit, because it's really important that this is being transmitted here. The key insight for these calculations is that in many problems for many data sets, we don't actually need a proper distance. It is perfectly sufficient if we have a weaker measure of some kind of similarity between data points or between data sets even. So hence, this is the I would say justification and motivation for all the other types of descriptors that we will find in topological data analysis. There are other representations of persistence diagrams, and they in turn offer such similarity measures, which in some sense scale better, so we can calculate them faster, quicker, and for bigger data sets. But of course, there is always a trade-off, and the trade-off here is that we trade some precision. So we might end up not being able to tell two things apart, even though their persistence diagrams are supposed to be different. Now, before we go into that, let me also tell you why persistence diagrams are relevant and useful in machine learning in general. I would say the main driver of topological data analysis in machine learning research is actually the stability theorem. And let me illustrate this intuitively here. So stability means that as we change our point cloud, as we change our input data to the persistent homology calculation, the resulting diagrams change in a continuous fashion, and they don't change very much unless we change the resulting point cloud. So for instance, if we do different samplings of the tori here, you can see that apart from one outlier, which I put here on purpose, these diagrams look more or less the same, even though the point clouds look a little bit different. So you can see that the sampling here is somehow different than the sampling here. But in general, you get similar results. So it's not completely off the scale. Now, of course, this is only true for small scale perturbations. And this, I have to say, is probably the reason why stability theorems are, I would say, among the most misunderstood theorems, or at least miscited and misquoted theorems in topological machine learning research at this point. Because people always say, oh, it's stable under perturbations of the data. But that's not exactly true. It's stable under small scale perturbations. So specifically, the diagrams satisfy a bound based on the Hausdorff distance. And that is all nice and good unless your perturbation becomes too big. So let me illustrate that with a circle here. So we have a circle here. You have your ordinary zero-dimensional homology, your ordinary one-dimensional persistent homology, as you would expect. So you find the cycle in the circle, as one would guess. If you sample the circle a little bit differently, that's still true. But if you add a couple of outliers that are really large in terms of the Hausdorff distance, right? So this is a very, very big perturbation that is done. You will find that suddenly the diagrams change. And notice that this change is quite drastic because I've on purpose, I used the same scales here. So it's all 0, 1, 2, 0, 1, 2 here. And you can see that this one cycle point that was so nice in the other data sets is suddenly gone, or at least its persistence is severely diminished. So we still find the underlying cycle. So persistent homology still works in this case, but we lose the information about the persistence, about the scales in which this circle appears, and that has some big ramifications. I do want to stress that here. It's not impossible to avoid this problem. So there are filtrations that you can pick that are more advanced and that are more stable to other types of perturbations, but it is a real issue. So if you think about stability, you need to think about stability in the small scale sense. Now, in practice, this is also something to be considered when working with persistence diagrams in a machine learning setup, because you need to be careful when you work with subsamples of a point cloud. So if you look at this curve here, if you have a mini batch size, so if you take progressively larger subsamples of a large point cloud, then you will find that the distance between the Hausdorff distance between those two point clouds, the original one and the subsample one, it goes down, but it goes down very, very slowly. So you need a lot of subsamples to get this down to some kind of manageable level. And this is just, I'm mentioning this as a practical insight for dealing with persistent homology in practical applications. You need to be aware of the fact that if your subsamples are all over the place, so if your mini batches do not capture the topology that you want to capture, then you end up having a bad time in terms of the distances that you can calculate. But that's all. That's not a problem for the applications that I will show. In fact, we can actually prove even. We will see that later. We can even prove that this works nicely. Okay. Now, having said all that about persistence diagrams and distances and stability, the main question that I want to answer next is, how can we use persistence diagrams as features to a machine learning classifier? What options do we have? And before we can answer those, I want to give a brief interlude on kernel theory. I know kernel theory is not maybe contemporary mainstream machine learning research at this point anymore, but it's still somehow relevant, and in particular it's relevant for the small scale regime and for the regime where you want to prove more theoretical properties of the resulting representations. So given some set x, we assume that we have a function that operates on tuples of x, so it maps x and it maps 2 points x and y into the real numbers, and we call such a function a kernel if there is an associated Hilbert space H. So on Hilbert space, meaning that we want an inner product space that is also a complete metric space. So it needs to be complete, it needs to be a metric space, and it needs to have an inner product. So we need this Hilbert space, this associated Hilbert space, and a map phi, which goes from the set X into the Hilbert space such that the function can be expressed as the inner product between the images of that map. So I'm going to let that stand for a second because it's a mouthful to chew on. So the function k, this evaluation k x y, can be written as the inner product. So here the L angle and right angle bracket of the images of x and y under this map phi. So phi is also known as the feature map, and k is of course known as the kernel. This is why it's denoted by k. Now this is all well and good. What can we use that for? Well, the great thing about kernels is that they can be used to assess the dissimilarity between two objects. So essentially the kernel permits us through this construction here, right, through this associated or also known as reproducing kernel Hilbert space, it allows us to lift the problem of comparing 2 points by evaluating this function instead of evaluating the feature map. So even if you have a very high dimensional feature Hilbert space H, we still know that the dissimilarity or similarity between 2 points can be represented by the kernel map here by k, by evaluating k of x and y, and this can be used to, for instance, simplify classification. Now, I'm mentioning this because, of course, there's a lot of things that map a persistence diagram now into kernel or into a Hilbert space, and one of my favorite ways of doing this is a work by Reininghaus and colleagues known as a stable multiscale kernel for topological machine learning. And it was really called that way, which is why I'm so excited about it, because they were really the first visionaries to see that this field might have some traction in the future. The kernel is defined, even though the equation looks a little bit weird potentially, the kernel is defined in a very simple fashion. Basically, for the kernel itself, you take points in your diagram. So you take a point P from diagram D and a point Q from diagram D prime. You evaluate some kind of weighted sum of dissimilarities or of distances between the persistence tuples, and you weigh that accordingly with respect to a distance that depends on the projection to the diagonal of the one point. You can even write down a closed form feature map expression, which looks not very dissimilar to the kernel itself. So that's of course not a coincidence here, and it's essentially also just an exponentially weighted sum of these distances. Now, the great thing is that Reininghaus and colleagues showed that this actually works, and this gives you a way to assess some kind of dissimilarity between persistence diagrams without having to solve an optimal transport problem. So this is still quadratic, of course, right? You have to move over the points P in one diagram and the points Q in the other diagram, but this can be made pretty fast. In particular, if you use some kind of nice tricks for speeding up Gaussian calculations and so on and so forth. So this is really simple to implement, and it's also expressive, as they show in their paper. Expressivity meaning that they can capture a lot of the variability in persistence diagrams and use it in a classification setup, for instance. Let me briefly illustrate what this feature map does, because I think the nice way to think about this is to say that it's a way to diffuse heat in the persistence diagram. So it treats every point in the diagram as a little bit of a heat source, and then it smooths over all of these heat sources. And this is maybe this is a little bit too illustrative here, but if you take this diagram here and you use a big smoothing scale, then you essentially end up getting this nice blob here. And you can see with this sigma scale that you can control the fact whether you're interested in larger scales or smaller scales. So sigma, of course, is typically set by some kind of parameter optimization strategy in your algorithm. So there's no canonical choice of sigma, but there's also ways to learn this parameter. And we can maybe have a discussion about this, because I might have some recent some new research soon about this. Now, there's of course other formulations of this. So again, I cannot claim that this is a fully comprehensive list, but these are most of the papers that I could find in recent years on additional kernels. Interestingly, and I mean, this is why it's called topological machine learning. Interestingly, all of those appeared in machine learning venues. So there is a small, but I would say vibrant community of people doing topological machine learning already and pushing this into the machine learning conference. So it is possible to do that. There is, for instance, a very nice paper by my colleague Mathieu Carrière and colleagues where they use slice Wasserstein distance calculations. So the sliced Wasserstein distance being a way to significantly speed up the Wasserstein distance by taking essentially one-dimensional slices through your distribution. There's also work by Cusano and colleagues on kernel embeddings. And there's even a persistence Fisher kernel by Lee and Yamada, which uses some concepts from Riemannian geometry. So all of these have different scalability, expressivity, and also stability properties. But in general, I find that they all operate under the same concept. So they make it possible for you to lift your problem into a comparison of high-dimensional vectors in some Hilbert space. Of course, there's tons of applications for that. So again, this is not maybe something that you would typically do now with a very big data set, but for small data sets, a very nice thing that you can do with these kernels is you can use kernel PCA, which gives you a way to do visualization, dimensionality reduction, or even feature generation. So essentially, if you plug that in, you get a way to simulate modern dimensionality reduction algorithms like UMAP. So you can take your data and compare it using the persistence diagrams. You can, of course, also do kernel support vector machines to do classification. That, I would say, is in fact the main reason for the existence of kernels in the first place, doing support vector machines and doing the so-called kernel trick of support vector machines. Or you can use a kernel support vector regression model for solving regression tasks. So the reason why I'm mentioning this is that despite deep learning being, of course, the prevalent paradigm at the moment in the whole of machine learning research, there's also other ways to go about this. And in some cases, not in all, but in some cases, using these classical machine learning techniques with a topological data analysis based feature generation method can be very, very gainful and still and lead to very, very good and stable results. Now, but that being said, the primary disadvantage of all these kernels is still their scalability, which means that unless you have a very specific model that circumvents that, or unless you use the feature map of the kernel, which gives you a way to featureize your data directly, you have to always calculate this pairwise kernel matrix between your data points. So essentially, even if you have a very quick, very fast kernel, you still have to evaluate them in a pairwise fashion, and that typically makes it very, very hard to scale this up to millions of data points. So there's a kind of a fundamental limit to the utility of those, but still they have their uses. Now, let's move on a little bit to other representations. So we've talked about persistence diagrams and kernels. What else can we do? Well, a very simple, and I should say probably still kind of my favorite representation of persistence diagrams is the so-called Betti curve, which is a very simplified representation of persistence diagram. It essentially maps a diagram to an integer valued curve. So it just measures how many points you have given a specific threshold. So you start with the diagram, you convert it to a barcode, and you start slicing that barcode according to the time, or the epsilon threshold, where the number of intervals changes, and then you just count the number of features that are active or living, if you want to use that more stronger word here, that are living at this time. So this gives you a very, very simple way to generate an integer valued curve from your data. And why should you do this? Well, the Betti curve is really nice as a topological descriptor because it's very simple and easy to calculate. It's really just, you take your diagram, you integerize it, if that's a word here, and then you're done. It also is a simple representation, which is often very good because it does not live in a very complex space. It lives in the space of piecewise linear functions, which is nice. So you get a function out of there. You can do things with these functions. We will see some examples in a few minutes. One of the things that you can do is you can do vector space operations. So for instance, you can do addition or scalar multiplications of these functions. So it gives you a way to operate with your representations. Moreover, of course, you can also define distances and kernels. So for instance, you can do a nice distance based on the area under the curve and so on. The downside is, of course, that there is no simple stability theorem. So in fact, I think it was work by Vidit Nanda and colleagues who showed that there is in general no stability for these type of curves. But I used the introduction of this lecture to discuss a little bit the aspects of stability. So maybe it's not a problem in practice that the representation is not stable under certain types of transformations, because you have to look at the transformations that you actually do, right? If you, for instance, see that it's stable under subsampling, that is already enough for many machine learning applications. You don't need to be stable to all kinds of perturbations. And yeah, and as I said, you can define distances and kernels. So one is very nice by basically taking an integral and with some proper parameterization and weighting. And we've looked at this a lot in a paper that took some time to come out. So this research was done in 2017, but it only came out in 2020. I'm just mentioning this because in the meantime, between writing this up and sending it out, a lot of people also did something with Betty curves, and so I don't want to claim that I'm the first one or the only one who did anything with this. At the time when we wrote this, we were the only ones writing this out, which also means that it has this weird title here, persistence indicator functions. We didn't really think ahead with this one, and so now the proper moniker should be Betty curves, I think. Now, let me show you how to use that gainfully in practice. So one thing that you can easily do is you can exploit the vector space structure by, for instance, doing a mean Betty curve that you calculate of your data set. So for instance, here we did this for a sphere in dimension 1, meaning that these are all the Betty curves of the dimension 1 persistence diagrams. And here we do it for a torus. And so you can already see that, not super surprisingly, but still kind of nice, you can see that these shapes, the mean shapes, are very different, and you can use those to, for instance, compare two distributions of data sets. Notice that this does not easily work with persistence diagrams. So it is possible. My colleagues, I think Mathieu Carrière and Theo Lacombe, have written something there. Maybe I'm mixing up the names. I can look this up later on. They have written a very nice paper on expected persistence diagrams and mean persistence diagrams and so on. And there are also matching algorithms here. But in general, I would say there's no straightforward way of doing this with persistence diagrams. Now, moving on from a very simple descriptor to a more elaborate one. One descriptor that I also very much like and that I've been using a lot in previous work is the persistence landscape. The landscape has this idea of using a kind of rank function of the covered topological features of a diagram. So you start with your diagram here, you kind of mark the area of influence, if you want to call it that, of your persistence tuple, and then you just count how many intersections you have in those. So here you would have 3, I think, and here you would have 2, here you also have 2, and here you have just have 1. And when you do this, you then just peel the layers off iteratively. So you start with a thing that has no intersections, then with 2 intersections, then with 1 intersections. And this leads to this very nice set of nested curves here. So you have the red curve, which is the first layer, you have the blue curve, which is the second layer, and you have the green curve, which is the third layer here. This formulation is due to a paper by Peter Bubenik, and the great thing is that persistence landscape have beneficial statistical properties, and you can also easily calculate or efficiently calculate distances and kernels. The minor drawback, I should say, is that if your persistence diagrams are very big, calculating all the layers of the landscape can take some time, but But Pavel Dlotko and Peter Bubenik have a paper on how to do this more efficiently. And I would say that in general, it's not a problem typically for your data, because you can still use the first 1 or 2 layers, and that is already enough in many cases. Again, for the sake of posterity and fairness, I also want to point out that this is really great work that appeared in the Journal of Machine Learning Research already in 2015. So clearly there is still a community and still a way to get these things into the machine learning community at large. Now, people are using the persistence landscapes in different ways. So what I've seen often in some of the packages that have been written, the software packages, is that the landscape is sampled at regular intervals. This gives you a fixed size feature vector that's really nice. So you can say, I want 100 samples of my persistence landscape, and then the feature vectors that you put in your model later on are always 100 dimensional. There's of course a very nice built-in hierarchy. So you can say, I only use the first layer, the second layer, and so on. The most important thing though is that it's a bijective mapping. So technically you can go back from the landscape, or from all the landscapes I should say, to the individual diagram. So this is really nice because technically, and again I'm stressing this here, there's no information lost. Whereas with a Betti curve you have your fiber, your pre-image, the pre-image of a specific Betti curve is much bigger than in the case of this bijective mapping. Moreover, and that is maybe relevant also for the data analysis aspects, is that you have stability theorems again. So the stability theorems hold, and it's in fact a very big aspect of this JMLR paper by Peter Bubenik. There is some work that shows that these persistence landscapes can even be used as a neural network layer. I'm not going to go into details here, but if you're interested in this, take a look at this paper by Kim and colleagues, which shows how to use, the persistence landscape as an efficient topological layer, meaning that there's a way to take those landscapes and put them directly into a neural network. We'll later on see more examples of this without using different descriptors. So we'll be dealing with persistence diagrams directly in a different fashion. Hence my emphasis on the diagrams in the beginning. But I want to point out that they have seen some incorporation in recent machine learning works as well. Now, I'm gonna move through a couple of other options for featurizing your persistence diagrams. There's a great work by Perea and colleagues on template functions. So here the idea is you take your diagram, you evaluate a template like a tent function on this diagram, and then you sum over multiple template functions to obtain a bigger feature vector. That's a very nice idea. That's a very nice concept that can be used to featurize persistence diagrams. There's also a histogram-based vectorization by Zielinski and colleagues, which involves clustering diagrams, learning representatives of these clusters, and then learning a bag-of-word representation of this whole clustering. And then the quantized bag of words, so the let's say simplified version of this bag of words embedding can be used as a feature vector. I do want to stress that a priori it's not easy to pick parameters here, and there's what I find personally lacking here is an intuitive description of the resulting representation. So I'm not sure what I would get from having clusters of persistence points here, but there are a lot of applications, and this is why I encourage you to read the paper. There's a lot of applications where these clusters actually have a lot of meaning. But I would say that in many of the data sets that we will be looking at later on, it's not a priori clear that you need a cluster structure, or that you can gainfully get something from there. Finally, of course, there's also, well, I should say finally, no, there's still a couple of minutes left, but the most important and I should say maybe even famous representation and featurization of a persistence diagram is the so-called persistence image. So this is a multi-scale descriptor that works by taking a diagram, projecting it down to the diagonal, and then representing it using a surface at various degrees of coarseness. So essentially you get some kind of probability distribution that is discretized on a grid. This is due to Henry Adams and colleagues, and it's a very nice way to deal with persistence diagrams in practice, because you can featureize this type of descriptor easily. It has beneficial stability properties, so they can show that this stabilization, this calculation makes sense. I also like the fact that it has an intuitive description in terms of density estimate, so it's a probability distribution that you evaluate. And well, the only drawback is that in practice, this resolution and the smoothing parameter, they are hard to choose, because the resolution of the image gives you directly a way to control the number of features that you have in your data set, which is very, very hard to know a priori. And the smoothing parameter is often also very, very hard to pick, or at least I should say, when I say hard to choose, I don't mean that it's impossible to choose them, but I mean that there are no canonical choices based on the data that you put in there. Of course, also, I should mention this, the representation that you get out of there is definitely not sparse. It's a full image, so it has quadratic scaling with the resolution R that you put in there, but you can easily use it in a classification setting. So in fact, this would be my suggestion to everyone doing this kind of thing. If you start with persistence diagrams, use the persistence image paradigm and throw those images into a simple classifier, and I'm sure you will find some interesting signal for your data. There's also extensions of those which I will not cover in a lot of detail. So for instance, you can learn metrics for these diagrams. So you can learn different weights based on the task at hand. You can learn a weight function on the persistence image and use that for the classification. This gives you a way to calculate weighted distances between images. This can be either used as a kernel in SVM or as some kind of predefined features as well. There's also work by my colleague Mathieu Carrière and colleagues based on the extraction of stable topological signatures. That's also a very nice way to featureize a diagram. So you essentially evaluate some kind of minimum functional that depends on the distances of points or the distances of points to the diagonal. You can sort all those values and then just pick the k largest ones of them. That gives you a very, very simple and nice way to featureize a lot of persistence diagrams. At the same time, it also has scalability issues because it scales quadratically with the size of the diagram. There's also we're almost at the end now for at least for this first slot. There's also a way to deal with norms of a persistence diagram. So we can use these norms like the infinity norm or the p norm. We can use those as summary statistics. And these are relatively useful. I would say they're stable and highly useful when you have a lot of persistence diagrams, for instance, that vary over time, and you want one nice summary to look into those. So we have been looking into this, for instance, in the context of analyzing fMRI data sets. And in this case, you can see that you have your time series here, and suddenly the norm spikes and then goes down again for a couple of those time steps. So you can easily see that there's something going on in the diagram, and you can look at this. Multiple curves, of course, being based on a summary statistic, can now be easily compared with each other. And so I would say that these summary statistics, if you have a time varying diagram, are an excellent proxy for complicated distance calculations. Now, we can do even more. So my colleagues Ilya and Vidit and Harald have a nice paper on a vectorization strategy based on path signatures. So there's a way to associate different paths in a diagram to a given descriptor. And then you can use the so-called path signature, which is a little bit like, well, it's a very abstract name for a very precise concept, right? It's a universal nonlinearity on the paths of bounded variations, and you can use this type of signature to compare the diagrams. One of the advantages of this type of vectorization is that you gain a lot in stability. One of the disadvantages is that they're very computationally heavy. So I like the results in this paper. I urge you to check this out as well. At the same time, I'm not sure how scalable this would be for bigger data sets, but maybe I could be missing something here in the calculation. Now, which method to use in practice? I think I'm gonna send the slides around so we don't have to go through this in detail, but I just want to point out that the main path that you will probably want to take is that if you want to do classification or visualization and you want features of your data, then just take the persistence images as a first step, right? That doesn't mean that it's the best one here. If you don't need features directly, but you're okay with distances or kernels or something like that, and you have large persistence diagrams, take the curves. If you have small ones, take a kernel. If you just want summaries, just take a summary, right? And if you actually want to do statistics, take the persistence landscapes. Although I should say that these are not set in stone, right? There's a lot more nuances to that. And for instance, we've been using the persistence landscape very, very gainfully in previous work when we were actually interested in classification tasks as well. So, but this could be a first hint for choosing these descriptors in practice. And now, some takeaway messages before we go into the break. So, the original persistence diagram, in a way of using this with air quotes here, is a little bit cumbersome to work with due to its multi-set structure. So you have these tuples, you have these different multiplicities. So it's not easy to throw this into a neural network. Hence, there are numerous other representations that you might take a look at. They are all for different usage scenarios. Two classes of methods exist that you might be interested in. The first one being kernel-based, the second one being feature-based, although the distinction is not a strict one, because some kernels also give rise to finite dimensional features. One thing that I left out here, because we're already approaching the 50-minute mark, right, is there's more ways of transforming diagrams or things in a persistence setting to other descriptors. Two very relevant keywords here that you might be interested in is are the Euler characteristic transform and the persistent homology transform. So both of those are based on persistence ideas, and they give you ways to calculate and compare different shapes. Now, thank you very much for staying with me for so long, and we're gonna take some questions now, I think, right?
Yes, so thank you for this very informative and exhaustive summary of the scriptures that was, I think, very useful. I'm sure there will be questions. Somebody in the audience was amazed by the fact that those things are not really recent. You mentioned several the scriptures coming from 2015, so it's already 9 years ago, right?
Exactly, yeah. So this is indeed, wait a second, maybe let me see. I'm sorry, I need to open the chat
Can
now.
you read the chat, or shall I read it for you?
Yeah, no, I see it. Yeah. Yes, this is from 2015, indeed. I don't know this. The participant is called iPhone, but so maybe this is the first AI that is part of the chat, right? No, just kidding. Yes, this I think. So we're how to say this? We're going to do a little bit of time travel here as well. So we're going a little bit back in time first, and I'm going to show you that there is already a very vibrant community for combining these things with classical machine learning algorithms. But then, of course, in the second part of the lecture, which is due to start soon, we're gonna go full deep learning, and we're gonna look into some things that we can do in a deep learning setup. Yeah, so this is but this goes to show that there is that there is an interest, and that these methods can contribute a lot to classical problems. I hope I can cover some of those in the second set of lectures. But yeah, I think it's really great to see that they have been around for a while now, and we're just now seeing that they really gain traction, which I think is also fair, because neural networks have been around since the 50s, or yeah, the 1950s, right? And we're now seeing the traction since like 10 years. Anyway, sorry, this is me
Now
rambling.
there's a question about the stability of trees drawn from a bunch of pairwise distances. I'm not sure if I understand the question. Maybe you.
So the question is, what do you see here? If you have a bunch of pairwise distances, trees can be drawn. How would you look at the stability of the trees? Well, I mean, you could look at the overall merging, so which points are being merged with each other. It's basically a question of a hierarchical dendrogram merge, right? Um, I think this would be one way to assess the stability. But if you're what might be helpful in this case, if you just have pairwise distances, you're dealing with something like a metric space, right? And so the better way to look at stability here would be to look at something like the Gromov-Hausdorff distance, which in fact is also a thing or a descriptor that persistent homology is upper bounded by. So I'm gonna maybe type that into the chat, Gromov Hausdorff distance. But yeah, I'm not sure whether I can add anything else to that question. I can look up the reference in the
So, so when you build these distances, we're using, it's like a high dimensional vector, and depending on the sampling, these distances can have some noise.
Yes.
And that's why I'm worried, like, how do if I make a tree and let's say I want to publish it, people say, hey, how do you know this is the best tree, or is it really reflecting? So I think there the stability questions come up.
Yeah. Yeah, then I think you need to look into the Gromov-Hausdorff distance, because I think there is a paper by Fred Chazal and colleagues. It's, I think, called Persistence Stability of Geometric Complexes or something like this.
Okay.
I can look up the exact reference. And this one discusses the stability of the Viatorius Rips construction, which is essentially what you're doing then, right? So
Yeah.
you're dealing with a set of distances, and then you want to say, okay, what happens if there's some noise in there? And
Yeah.
then the natural comparison partner is indeed the Gromov-Hausdorff distance between two metric spaces. Unfortunately, the Gromov-Hausdorff distance is very, very hard to calculate in
see.
practice. But you at least get this as an upper bound. So basically, if you have, let's say, a nice bound on the diameter of your data, then then this will be useful. So I hope
Great.
that helps.
Thanks. Yeah. Thanks.
Yeah, you're welcome.
But yeah, at the beginning, you said that stability is often misquoted. I'm not sure if I understood what is the subtlety there.
Yes, I'm probably because you understand the theorem, but so one of the things, I'm sorry, I have to jump through the slides here now. I think newcomers to the field might often misunderstand the stability theorem, and they might think that stability means that it's really stable to even large scale perturbations, as long as there's not a lot of them. So basically, if you have one outlier, they will still say, oh, okay, it's still.
No, of course, no. Yeah. Outliers really make a big trouble. Yeah,
Exactly,
yeah.
but this is I think the subtlety that because you understand the theorem, this is I think something that is glossed over a little bit in the community at times. So I mean, it's not necessarily the reader's fault or the fault of the authors, right? It's just that it's a subtle point to grasp in the beginning, because you just read this and you see that, okay, there's some infinity distance between functions, but what does that actually mean, right? And so this is something that that I find is often surprising to people in practice, that they have that even one outlier that is kind of appearing on the large scale can destroy everything. If it's an outlier that it appears on the small scale, right, then it's okay.
But an outlier, indeed, it makes a big change in Gromov-Hausdorff distance. And maybe this is a weakness of TDA in this respect. It's very sensitive to outliers, right?
Yes, exactly. Yeah.
How does one identify outliers? There's a question in the chat again from Rabi.
Yeah, I think the easiest way would be to use some kind of outlier detection criterion based on something like the interquartile range. But okay, topologically it's harder. I mean, what you could do is if you have infinite compute, you could run the persistence calculations while always removing one point, right? And then you could see whether the diagrams change a lot or not. that would be a simple way of looking at it. I think a priori there is no canonical way of deciding what is an outlier because it depends on the application at hand. Yeah, sampling can definitely help, or subsampling, right? I mean, if you this is one of the reasons why machine learning works. We will see that in the next lecture. So if you constantly work with subsamples of your data, the probability of having the outliers, of course, very, very small, right? Because you typically assume that you don't have a lot of outliers in your data. Because if you have a lot of outliers in your data, then they're not outliers anymore, but they are your data in a sense, right? So hence, if you do subsamples, it's very likely that you will end up having a nicer a nicer structure. Of course, you then might also miss some of the small scale features, and you can, I think, see this in this slide a little bit. That depending on how you sample, right, you might end up getting these spurious coordinates here. Although I should say that these tori are not really sampled in a nice fashion. So I just wanted to illustrate the problem.
Bastian, I have another question. Somehow I had myself a wrong idea that a persistence image was obtained in the same way as you described the Reinickhouse kernel. So by letting somehow the Dirac distributions melt down until a certain stage. But you said it's a different thing. So persistence image is a different thing from a kernel, right?
I would say so, yeah. Although maybe one could show that it's potentially the same thing if you choose the weight function in a similar fashion. So I think you can construct the I think you can construct a persistence image using the persistence the multi-scale kernel weight function. That I think should be possible. Yeah. But these were developed concurrently, or I should say, also going into a little bit different directions, right? But I think Henry and others described this as a way to use a general probability distribution on the data.
So there is maybe one last question in the chat. Can you elaborate a little bit on the different sampling methods and which ones would be appropriate?
Oh, well, that's a good question. So I mean, I would say when I do deep learning, and I'll show this in a couple of minutes, I would essentially just always do uniform subsampling, what machine learners often call mini batches. So I would just basically say I assume that all my points are created equal in the point cloud, for instance, and then I just take a uniform choose them in a uniform fashion. I don't know actually whether there is research on the impact of different sampling and what it does to the persistence diagrams. But this would be interesting to try out. But it's not exactly my wheelhouse if I'm honest. It's not. It's a little.
Bastian, it's 7 o'clock, but maybe you need 3 minutes to drink a glass of water. So maybe we can have a very tiny break, a real break. I mean,
that would be nice. Yeah, I'm gonna.
Just feel free to return after a couple of minutes. So we'll start when you are ready. Just take your time, maybe.
Thank you. Yeah, I'm gonna take something to drink and then I'm gonna be right back.
So we wait those 3, 4, 5 minutes. Just
okay, but let's get back to it. In the second part of the lecture, I want to talk about autoencoders and inverse problems. So we're now going a little bit more deeply into the deep learning landscape. And I want to start by briefly summarizing some facts about deep learning and classical machine learning, because like in the Shakespearean play of Romeo and Juliet, these are two households, but they are both alike in dignity. So I really don't want to say that one needs to be preferred over the other. It all depends on your context and on your data. So classical machine learning techniques typically have one thing going for them, namely they are somewhat better interpretable often. They typically also work well in the small sample regime and have low requirements on compute, so you can run them on small devices, for instance. Deep learning, on the other hand, is often, but not always, like a black box. It requires large amounts of data and it has high compute requirements. So you have to pick and choose and be aware of those. Now, classical models are often not as easy to train because they require you to think about the features that you put in. They require so-called handcrafted features. Deep models, on the other hand, and this is, I think, one of the reasons why they fly and why they took off so nicely, are learning the features that they need for a specific task, but by contrast, they are also harder to investigate a posteriori. So you have to think a little bit more about what the actual representations mean. Now, it's not clear when to pick one over the other. I just want to give some anecdotal evidence that it can still happen, that it works or doesn't, right? So for instance, my colleagues, Köhler and colleagues have looked at cell type annotation in a preprint from 2021. It said, after evaluating 10 classification methods across 14 datasets, we notably find that deep learning does not outperform classical machine learning methods in the task. Okay, so one piece of anecdotal evidence that it's not always required. In our own work by my colleague Michael and a couple of colleagues, we looked at some kind of patient classification, and as we wrote in the paper, one of the most surprising results is the highly competitive performance of our DTW KNN classifier, whose performance for earlier horizons, so that's a prediction horizon, exceeds all of the other methods despite its conceptual simplicity. So again, this shows that there's still ways where your classical models can outperform more elaborate ones, but you really need to check. You really need to pick and choose and really need to be somewhat proficient about it. Now, before we get into how topology can work with deep learning, let me give you a deep learning crash course. And this is really a crash course, because if you just follow these instructions, everything's gonna crash, because it's really not enough to turn you into a professional, unfortunately, but I hope that it can give you the right vocabulary to look at things. So first we need to take a look at some terminology. So the phrase or the word batch or mini batch is often used to just refer to a subsample of the data set. So machine learners think of batches and mini batches instead of full data sets. The epoch is the number of times the entire data set was processed. So you throw your data set into your neural network model, and then you repeat this a couple of times in order to get better representations. The loss or the loss function is a function that determines how well your network fits the data. So this is where you have some ways to adjust your representation to the task, right? You can pick a loss that measures, for instance, how well you classify things, but we will also see some additional examples for this later on. The main thing, and this is why it's framed for you to remember and for you to understand, is that all of this type of training is possible because of a concept called backpropagation. So backpropagation is the algorithm that makes deep learning work and fly. It's an algorithm that permits you to adjust weights, that means the connection strength in the neural network to minimize the error. So you compute a gradient of the loss function for a specific batch, and then you update the weights afterwards. And all the magic, well, I'm glossing over a lot of details here, but all the magic of deep learning lies in the fact that you can do this backpropagation in a task-specific fashion and adjust the weights of your neural network so that they fit nicely with the task. Of course, there's many things to consider here, like things like overfitting or underfitting and these sort of things, how to choose a learning rate, which means how to choose the update size, the step size, and these sort of things. We're going to ignore all of those, but I just want to give you a conceptual overview of how deep learning works in practice. Now, what you will also find when you do some deep learning is you will find that there are some common architectures that people often talk about. One is the so-called fully connected neural networks. These are in a way the precursors to the current neural networks. So every neuron in this neural network is connected to every other neuron. There's convolutional neural networks, of course, which use small scale feature maps to work over images. There's autoencoders, which are a whole other class of neural networks, which we will be looking at now in this lecture. And there's recurrent neural networks, for instance, that learn a sequence of time steps, for instance. Now, there's much more. There's, for instance, the famous transformers architecture, but I can't put all of this in this one lecture and still cover the most relevant things. So this is where we have to be. Now, let's take a look at autoencoders, because that's the main paradigm that we'll be dealing with for this lecture for some time. An autoencoder is a network that consists of a couple of neural network layers. So here you can see these as an example. So these are the input neurons. Then you go down a little bit, you reduce the number of input neurons, you go down even further, and then you go back up again to the output neurons. The space X here represents the input data. This can be anything, but we'll typically assume that it's something like a point cloud, for instance. Z, on the other hand, so this thing in the middle, refers to the so-called latent representation, or also hidden representation, depending on what type of paper you're reading. And X tilde refers to the reconstructed data. Now notice that typically D, so big D, is much, much larger than small d, meaning that you go from a very high dimensional space to a very, very low dimensional space, lower d here in the middle, and then you go back up again. Why are you doing this? Well, you use a loss function, L, to measure the quality of the reconstruction. So you start going from X over Z to X tilde back again. Now, again, why would you do this? Well, this is known as a simple encoder or decoder architecture. And in some sense, you're learning the identity function. You're kind of just learning how to encode your data and how to decode it again, right? The middle layer that you saw here, so the one that I denoted by Z, the latent representation, is often known as the so-called bottleneck or the latent representation. And this latent representation is used for visualization, for interpolation, for clustering, or many, many, many other things. And it's really, really interesting. I want to emphasize this idea of the bottleneck here. So by squeezing your data through a very, very low dimensional representation, the idea is that you force the neural network to pick up on relevant features in the data so that the whole data can be reconstructed again. So a very simplistic example, if you had a data set that can be technically reconstructed by just 2 parameters, then regardless of how big your ambient dimension of the input data is, you could throw this into a 2-dimensional bottleneck and still be able to reconstruct your input data nicely from it. So hence the hope of people working with this type of technique or with this type of model is that you can indeed reconstruct the most relevant parts of the data from the bottleneck representation. As a very simple example, you could have a simple autoencoder that has as an encoder a linear transformation going from a high dimensional space RD to R2, and as a decoder you could have another linear transformation going from R2 to RD back again, and as a loss function you could use the mean squared error. And this is something similar to 2-dimensional PCA that you will get. So in a way you can think of autoencoders as a very general, very flexible way of doing PCA with high dimensional data. Now, let's make it topological. Let's talk about topology and how to bring this into the mix. One of the things that I will be talking about here is our paper on topological autoencoders, which is also called Topological Autoencoders. It's joint work with Michael, Max, and Carsten, and it appeared in the 2020 conference on machine learning. So the motivation is very, very simple. Let's hope that this video plays. Yes, perfect. So suppose you start with a data set that has a very specific type of nesting structure. So you start with a very big sphere, and inside that sphere you put a lot of small spheres. You can do this in high dimensions, right? And you have this very, very nice nesting relationship. That's an example of I would say, not entirely manifold data set, but still a data set that has locally, at least if you look at the right scale, it has some kind of manifold structure. But interestingly, if you use simplistic standard autoencoders, you will find that their latent space visualization, I'm going to show you a video of the training process now, the latent space that you look at, so that the two-dimensional space that you use for the visualization, for instance, is not able to show and preserve the relevant features. So you can see this here, that these points here are the individual spheres that are packed into the larger sphere in the middle. And you can see that the autoencoder rips all of those apart. So it's incapable of showing these these nesting relationships. However, and that's maybe the spoiler of what we can do, if we do this with the topological autoencoder, you can see that these spheres stick together here. I'm sorry for the for the performance here. I'm gonna have to switch slides soon because for some reason it doesn't nicely work. You can see that the topological autoencoder preserves this nesting structure. So it constructs the big sphere around the smaller spheres. So this is where we want to go. And how do we achieve that? Well, this is a diagram that I'm just gonna leave here for a little bit in order to discuss it with you all. We actually achieve that by just changing the reconstruction loss a little bit. So on the bottom part of this figure, on the top part of this figure, you find your classical autoencoder. You have the input data X, you push it through a neural network, you end up having a latent code Z and a reconstruction X tilde, and you measure the utility and the accuracy, if you want, of this reconstruction by evaluating a reconstruction loss. And now what we did is we added a topology-based loss to the autoencoder by taking the persistence diagram of the input data X, the persistence diagram of the latent code Z, so of the latent representation, and comparing those two diagrams with the topological loss function. The idea being that we want the topology of the latent space to fit the topology of the input data. So again, let me repeat this. We want to preserve topological features coming from X. We want to preserve them in our latent representation in Z. And then, of course, by transitivity, we also want to preserve them in X tilde. But primarily, we are talking about preserving them in Z, in the latent code, because that is the thing that we use for visualization. And that's essentially the whole idea. You can also see that we didn't really specify what type of architecture we're using. We can add this to any type of architecture. And let me show you why this works and why it's a good thing to do and what nice properties we can have for this. So the main intuition is that we align the persistence diagrams of an input batch and of a latent batch using a loss function. And this works in theory because we can actually show that even if we subsample our diagrams, even if we subsample our point clouds, we can still bound the probability of the persistence diagrams of the subsample exceeding a threshold in terms of the bottleneck distance. So this works nicely. Let me summarize this theorem. Is a little bit easier to summarize. In other words, the mini batches that we're looking at, they are topologically similar if our subsampling is not too coarse. So if we don't, if our mini batches are very, very small, then of course we might end up missing some things. But if the subsampling is not too coarse, we might end up seeing how these diagrams work. All right, now second part that we need to discuss. So this is why it works in theory, but how do we actually get a gradient to be calculated through this? Because that's the whole thing, right? I mean, everything has to be differentiable, and we have to backpropagate information through that. So it has to work out somehow. So to do this, we take a look at the distance matrices that we use for calculating persistent homology based on our data, and then we observe that under mild conditions, so under the condition that all the distances are unique, we can map each point in the persistence diagram that we get from this data. We can map this to one entry, exactly one entry, or rather, okay, in this case it's two entries because it's symmetric, right? But we can map it to one entry in the distance matrix. And moreover, since each of these entries is a distance, right? It's a distance matrix, so each of these entries is calculated based on two data points. It can also be changed during training. So at least in the latent space that we use, we can use the distance and change it using gradient calculations. Now, what does this mean? This means that we can set up a loss term based on persistence diagrams, or rather persistence pairings in this case. This is a lot to take in, and so I'm just gonna discuss the overall shape of things, as it were. So our main loss term consists of two components. One loss term going from X to Z, so from the input space to the latent space. The other from Z to X, from the latent space back to the input space. But they are virtually similar. Let's just discuss the first one, going from X to Z. So this is evaluated by essentially calculating 1/2 of the squared Euclidean distances that we get when we take our distance matrix here in the input mini batch, and we subset that distance matrix using the persistence pairing of the input mini batch. So the pairing means that we just take a look at which point is paired with, which simplex in the persistent homology calculation is paired with another simplex. And we can use that to subset the distance matrix, because if we stay in dimension 0, we know that every vertex has a corresponding edge thanks to the persistence pairing lemma. So we can calculate this. And then we subset the matrix of distances in the latent mini batch with the same persistence pairing, and we compare those. And now, vice versa, I should say, it works for the loss term that goes from Z to X. So we take the distances in the latent mini batch AZ here. We subset them using the persistence pairing of the latent mini batch, and we subtract the subset matrix of distances in the latent in the input mini batch again. So this is a bidirectional loss, as we call that, and the idea is that we take the persistence pairing. One time we take the pairing in the input mini batch, pi of x. The other time we take the persistence pairing of the latent mini batch, pi of z, and we take a look at how much the distances are changing as we exchange those persistence pairings. So I do want to stress one thing here. This is not a distance. So what we're calculating here, this LT, this loss term here, is definitely not a distance, because we are essentially using the wrong type of information for it to be a distance. We are mixing two distance matrices, one for the input, one for the latent code, right? We shouldn't be allowed to do that if we were interested in calculating distances. But I said this in the beginning of the first lecture already. In machine learning, oftentimes you just need some measure of similarity, and this is a very nice measure of similarity between the two spaces, or rather between the two persistence diagrams of the two spaces. And so it works very nicely in practice to give us a way to adjust our distances when training the autoencoder. And let me show you how this looks for a qualitative evaluation. So this is the same data set that I showed you in the beginning. Recall that this is based by taking a large sphere and putting some smaller spheres into that. We can embed this using a multitude of algorithms: PCA, UMAP, ISOMAP, t-SNE, the original autoencoder. We can all visualize the two-dimensional embeddings. You can all see that every one of those methods has a different way of looking at things, has a different way of emphasizing certain structures in the data. And the topological autoencoder is the only one that manages to put the spheres nicely together. So that's the qualitative evaluation part. Now, for the quantitative evaluation, I don't want to throw too many numbers at you. I just want to tell you here with this slide that this was really, really hard to evaluate, because when you're only looking at the reconstruction loss typically of your autoencoder, you can't really gauge the quality of the resulting latent space. And so we had to also think about new measures for gauging the quality of the latent space. We found a couple of those measures, something like continuity, trustworthiness, mean relative rank error, or a Kalbeck-Leibler divergence between density distributions. And the point I want to make with this is twofold. First, in many cases, or many data sets, I should say, the topological autoencoder is either the first, so this is underlined and bold, or the second, so this is just bold. It's either the first or the second best method of the batch of the comparison partners. So that's good, but moreover, it also does not substantially change the reconstruction loss. So we don't end up sacrificing too much reconstruction quality by using the topological autoencoders framework, which is the relevant thing to consider, right? If you use an autoencoder and you train it, you want to have good latent spaces, but also you want to have good reconstruction, because otherwise it's a little bit weird. So that's about the quantitative evaluation. Now, let me summarize what we have seen about topological autoencoders. We can make any autoencoder, any architecture, we can make it respect topological features, as long as we have a differentiable loss function. So this is most useful actually when multi-scale features of the data are relevant and need to be leveraged, for instance, in single-cell data sets. But of course, if you don't assume that you have multi-scale features in your data that are relevant, then of course you don't benefit from this method. I also want to point out great work by my colleagues, Ilya Trofimov and colleagues, who have an alternative or an extension, depending on your point of view, to this. There's different ways that are explored for matching the persistence diagrams. This is very recent work from last year's International Conference on Learning Representations. It's called Learning Topology Preserving Data Representations. And it essentially continues our work and shows where the topological autoencoders framework can fail, in what configurations it fails, and how to address and solve that. So it's really nice work, and you should consider checking it out. About the first point on this slide, I do want to stress that this is really, really fun if you think about it, because in the appendix of our paper, and unfortunately this is I'm going on record with this now since this is going to be recorded. This is an unfortunate tendency in machine learning research, is that your paper is actually just 8 pages or 10 pages, but then you have a 30-page appendix. So the real interesting stuff happens often in the appendix, and so it is in our case, I would say, because we have some results in this topological autoencoders paper where we show how to, for instance, topologize, if you want to call it that, topologize PCA. So that's really, really cool. We can literally take anything that you can represent as an autoencoder, and we can make it a topology preserving to a certain extent. So that's it's a really nice generic framework. Now, moving on, I want to stress that this is actually an instance of what I would now call a generic topology-driven machine learning pipeline, and this is only possible because of some crucial insights by a lot of people over the past couple of years. So your traditional persistent homology, or I should say topology pipeline, maybe works by taking a point cloud, doing persistent homology, which I always describe as a coffee grinder, because it helps you extract the real interesting things from your data, right? You get your persistence diagrams or other descriptors, of course, and then you do the machine learning. So this is the traditional way of doing things, right? You take the diagrams and then you somehow featureize them and put them in a machine learning model. But this is not all there is. So actually, as I said, there's a lot of people contributed to this, and there's a crucial insight that if you want, you can reverse all of those arrows, right? You can actually back propagate information through this whole pipeline. That is very specifically said, a gradient through this pipeline. So going from the machine learning model and its internal representations back to your point cloud, back to your input data, typically exists under certain mild conditions. And there's some works that looked at this. I'm going to start with the most relevant one and the most famous one, I should say. So Mathieu Crayer and colleagues have written the definitive guide on this. It's called Optimizing Persistent Homology-Based Functions, and it's also an ICML paper. So they showed essentially what type of functions and functionals based on persistence diagrams you can optimize in such a fashion. And then, of course, you have our Topological Autoencoders paper, but there's also a great paper by Poulenard and colleagues on topological function optimization for continuous shape matching. And all of these works have one thing in common, namely they show that backpropagation works. As I said, the most general one, the most generic one of these works is the one by Mathieu Crayer and colleagues who actually push this to a new level and to show that a lot of the things you can do with diagrams actually result in a nice gradient. I'm emphasizing this idea of the gradient so much because if you do this right, if you implement this in software, many of the deep learning frameworks already have built-in automated gradient calculations, which is great because that means that you don't have to think about where the gradient is actually coming from and how it works and how it goes through the network and so on. So this is really great if you want to build your own architecture and build a bigger machine learning model from that. Then you literally don't have to precisely think about how to calculate gradients, which is why that is such a big deal. Now, as we move towards the end of this lecture, I want to show you another case where instead of dealing with point clouds, we're now dealing with images. And I want to show you what topology can do in this case. I use the umbrella term using topological information for solving inverse problems here, because what I'm going to show you is indeed an inverse problem. So this is joint work with a couple of people, but most specifically Dominic and Karsten, and it appeared in MICAI 2022. Now, the goal is to do cell shape prediction. So complete different set of rules, complete different set of things. We use a confocal fluorescence microscopy device to obtain images of cells, so like actual living cells in a human body. And we are interested in understanding the 3D shape of a cell. So really like literally taking some slices and images and then turning those into a 3D model. This is also known as morphological analysis of cells, and it's crucial to detect certain pathologies. So to quote, for instance, from a paper by Ford, when used properly, red blood cell morphology can be a key tool for laboratory hematology professionals to recommend appropriate clinical and laboratory follow-up and to select the best tests for definitive diagnosis. So this is really an issue, and I want to stress, I mean, we're not near we're not near rolling this out into the wild yet, but the idea would be that blood is a very simple substance to get in a hospital, because typically every patient can at least spare a couple of drops of blood, right? So we're not talking about liters, we're talking about some drops of blood. And if you get those drops, you run them through confocal fluorescence microscopy, you obtain some images of the cells, and you look at the 3D shape of a cell. You can very rapidly, very quickly, and moreover, very painlessly do an analysis and a pre-screening for certain pathologies. That will be the goal of our work. So you can take a look at the red blood cell morphology and figure out whether the patient, for instance, is suffering from anemia or from certain or even from cancer. All right. How do we do this? Let me show you the whole model or the whole diagram and how it works or why it works. So it's essentially a complicated inverse problem because we want to go from 2D to 3D, right? So we have one image and we kind of want to reconstruct the full shape from that. So to do that, we use some kind of machine learning model, which I leave open how that looks, although I'm going to show you a suggestion later on. We do a 3D prediction, and then we can compare this prediction to the ground truth using a geometry-based loss. We'll see examples of how this works in a second. Now, this was the first part of the pipeline, but it did not lead to satisfactory results. And instead, what we did is we added topological features again. So similar to the topological autoencoders, you can see that they're kind of the same in spirit, which is why I put them in this presentation. We take our 3D prediction, we look at its topological features, and we compare those topological features with a topology-based loss and the topological features of the 3D ground truth. So again, this is a complicated inverse problem because you go from 2D to 3D, but if you can solve this efficiently and in a trustworthy manner, then it's a great step forward. Now, the main architecture that we used for doing these predictions is some kind of convolutional architecture with a fully connected neural network on top. So the exact details are not relevant here, but let me tell you that we are essentially with this method learning a likelihood function. So likelihood function that lives on a cube space or on R3, and it lives on this voxel grid, and it assigns to each voxel, so to each point in R3, it assigns a value that indicates the likelihood of this voxel being part of the true volume, so of being the true shape. And this is a very nice way of that we can use for topology-based calculation, because as you've heard in the previous lectures, there is it's a very general concept. You can calculate persistent homology based on a lot of input data sets, and indeed you can also calculate it for 3D volumes, and that is the main insight that makes this method fly. Now let me show you briefly the loss functions. So the intuition behind the geometry-based loss functions is that we want to capture and compare the geometry of the resulting volumes on a per voxel basis. So we want to see whether the reconstructed volume is well aligned with the ground truth one. So to this purpose, we use a binary cross entropy, for instance. So that's not very specific. It's a very general way of dealing with image-based data. But here I want to briefly show you how we make it topological. So our topology-based loss between the two likelihoods functions f and f prime living on the same space or on the same grid uses a sum of a Wasserstein distance and a sum of a total persistence, so sum of a norm in essence of the respective persistence diagrams. And there's two parts to this. The first loss component, here marked in red, is meant to align the ground truth likelihood f and the predicted likelihood function f prime. So that's your usual Wasserstein loss, right? We just take a Wasserstein distance, we align those two persistence diagrams, and then we're done. By the way, computationally this works because the volumes that we're looking at are not really big, so we can still solve the Wasserstein optimization problem quite efficiently. The second part is, however, the one that I find very intriguing. The second part uses the total persistence, or some kind of norm, of the predicted likelihood function f prime. And that is indeed a very nice way to reduce the variation of geometry and topology of this function. So it encourages the model to have a likelihood function that doesn't have a lot of, let's say, small scale features across the boundary of the object, for instance, because red blood cells typically don't have those, right? They are very, very smooth. And so since the loss is going to be minimized in the end, this encourages the model to learn a sparse representation here that doesn't have too many spurious topological features. Now, then we do the usual thing. We combine this loss term with our geometry-based loss term by choosing some kind of scaling parameter lambda. And let me just show you that this works really, really well. So we have a quantitative evaluation on two data sets, and in almost all interesting metrics that we're looking at, the addition of the topology-based loss term indeed results in higher quality results, and moreover, at almost no additional performance degradation, because the persistent homology calculation is actually faster in this case than the actual training of the neural network. Now, that's of course not always the case, but since we can control the volume size and so on, and the calculation of the persistence diagrams, we actually end up not making the model substantially slower by adding this additional loss term, but we gain a lot from it, as you can see from these results. Now, that brings me to the end of this lecture. What I want you to take with you from these two examples is that these are examples of topology-based loss terms. So next time we will be looking at more complicated models where the topology is kind of intrinsic and inherent to the model. But even so, even by just looking at a topology-based loss term, we find that those are helpful in regularizing models in practice. And next time we'll also tackle more and different modalities. So here it was just point clouds and structured data like images, but we can also tackle other modalities like graphs, for instance. That brings me to the end. If you want more information, you can of course send me an email or check out the website of my group, idos.group, or my own personal website. And if you have feedback about this talk that you don't want to write in person, then I also have an anonymous feedback from these days, which you can find here. And I'm mentioning this so prominently because I think it's important that that there's a way to give me feedback that doesn't necessarily have your name attached to it. But if you want your name attached to it, of course, and you want to say something nice or something not so nice, then you can also shoot me an email. Okay, thank you very much for having me, and yeah, I look forward to your questions now.
Give me applaud. I mean, that was really amazing, inspiring, informative. Well, there are already questions in the chat. One was asked at the beginning of your talk about the training. Maybe you can read directly from the chat.
Yeah,
are you training based on the Z rather than the output? But this was long ago.
Yeah, this was for the topological autoencoders. So no, we don't. For the training, we still use the reconstruction, right? We just have this additional loss term that injects information about the latent space into the training. But we still train the overall autoencoder architecture based on the usual loss between X and X tilde. So
but in the middle, you seem to be injecting the topology into the Z somewhere. I saw a formula for that.
Yeah, no, that's true. We inject it into Z, but for the training of the full architecture, we use X and X tilde. So it's kind of a fun way. It's similar to this one here. We have this dual loss term, one that takes care of the geometry and one that takes care of the topology, and they operate on slightly different parts of the data.
So you calculate also just want to clarify, just want to understand. So you calculate the persistence of the Z layer and then add it to the output layer as a loss?
Yeah.
Okay. Thanks.
Exactly. And interestingly, I want to stress that we haven't actually looked at this. This just it occurred to us afterwards. But then, of course, I mean, you need more time to do even more research, right? But it is also possible to just compare X and X tilde in a topology base. So if you do this, then you would end up having a reconstruction objective that is supposed to preserve the topological features in the data.
Wouldn't that be easier to do and more
yes,
consistent?
It would be. It's just that if you do it like this, if you do X and X tilde, you don't necessarily get the guarantee that that your latent representation contains interesting features or topologically correct features in a way. So that's the thing that we wanted to solve.
There are other questions in the chat. Wouldn't the orientation of the 2D projection be critical for the inverse mapping?
Yes, indeed. That's also one of the reasons why this is really hard. Depending on how you slice the cells, you might end up getting a very bad projection that doesn't nicely work. So one of the things that we could do is we could have lots of those, right? We're not only doing the reconstruction of a single cell, but we're doing the reconstruction based on multiple cells, based on a lot of cells. So we hope that we can mitigate these problems somehow. But yeah, indeed, ideally you would have multiple slices of the cell. But the thing is, if you do multiple slices of the cell, it also takes longer, the procedure. So there's a trade-off between having a quick test in the hospital or something that is very, very precise, but also takes much longer. So it's in a sense we're kind of between two extremes here with this work.
Some people are asking whether there is a Python notebook to make it more practical for the autoencoders and SHAP, or is there a GitHub for the code? Another participant asks.
There is GitHub for all the code. So if you look at either my website or my group's website, eidos.group, you will see that for almost all publications, well, not for all, okay, for all the publications, we try to have a link to the code so you can directly click on those. Yeah, I don't have a specific notebook for the for autoencoders or for Shaper, but both of those are available on GitHub, and you can directly work with them. Yeah. Now there's one question about taking the persistence diagram into machine learning. Well, there's multiple options, some of which I mentioned in the lecture, right? So here you can see, in this case, you can see that I take the persistence diagram only implicitly into machine learning. So I use a Wasserstein-based distance between them and so on. If you want to actually work with persistence diagrams, one thing you can do is use what is known as a set function. So we can learn a function that essentially maps a set of points to a high dimensional vector. Or what you could do, I haven't shown this here actually. I was going to show this in the next lecture, but I'm going to spoil it already here. There are so-called layers that can take persistence diagrams as inputs and then give you a high dimensional vector representation for a neural network. One of those is, I think by my colleagues, it's by, let me think, it's Hofer and Quit, deep learning with topological descriptors potentially. I'm not sure whether I'm getting this right, but it's definitely in Europe's paper from 2017. So they have a very, very nice layer that works with persistence diagrams directly. Hope that helps. But I'm going to cover some of these aspects in the next lecture as well.
Well, one question. So the topology-based loss terms that you have described, if I understood correctly, they are focusing on the topology of the data. But maybe there are other ways of using topology for regularizing models, which are more indirect. I mean, based not on the data, but something related to the architecture or activations of the network.
Yeah, that's a very good question, or a very good observation. I have no easy answer to that. I can just say that there's many more things that one could do. I have some early work on what we call neural persistence, which is a way to look at a whole network as such and look at the weight structure of the space. That is something that I'm seeing other people are also doing nowadays. So looking at how the weights, how the internal representations of a neural network change. That would be one way where one could use topological features or topological information. Next time, I'm also going to show a couple of ways to incorporate it directly into a message passing neural network, for instance. But yeah, it's a vast field, and I think we haven't even discovered all the relevant ways of working with this yet. There's also work, for instance, on boundaries, on the classification boundaries and how to regularize those. This is very, very exciting to me because it can be used to have nicer decision boundaries essentially between models.
That's a nice question in the chat.
Yeah. Is there a way to also include the second derivative in the Wasserstein distance? I'm sorry about this. This is actually not a derivative. This is just the prediction. So I'm using f and f prime as specifying f and the predicted function. The prediction is called f prime. So this has nothing to do with the derivatives, unfortunately. Yeah, it's a good point. Maybe it would be better to use a different terminology here. But I always like to use it f and f prime to show that kind of f prime is somehow related to f, instead of saying okay f and g or something like this, right? Maybe f tilde would have been also good. But yeah, no, it's not a second derivative.
But the f prime, how do you estimate? Isn't that based on some kind of like is it like a derivative approach?
So sorry, I didn't catch that acoustically. What are we estimating?
Yes, the f prime. What is the formula for the f prime?
Okay, yeah. So I mean, f prime is the predicted likelihood function that the neural network learns. So essentially, the thing that comes out of this model here, this gives us a prediction for the full volume, and this tells us where the voxel what the probabilities of a voxel being there are. And this is how we use it. We train that neural network with the standard geometrical laws, so with binary cross entropy and these sort of things. So here with the dice laws and binary cross entropy.
Thank you.
Welcome.
Okay, I think we are close to end. Bastian, maybe I don't know if I can ask you to make some propaganda for next week. So maybe you don't want to make a spoilers, but just maybe a small announcement of what topics are you going to cover next week?
Oh yes, so yes, of course. So next week I'm going to talk about graph neural networks, so message passing neural networks, and I'm still a bit on the fence whether I will also include this, but I think there might be times I'm trying to squeeze it down because I have many topics. But I will also talk about work on shape classification with persistent homology and on and work on singularity detection using local persistent homology. So basically covering all the things, going from the data to the models, and then back to the predictions.
Okay, that looks exciting. So Aniceto is not here this week, but let me close the session by thanking you warmly for all the effort and for the wonderful explanation. I mean, I learned a lot, and I assume the rest of the audience also enjoyed it. Anyway, as we said, the recording will be in the website maybe within 24 hours. And if you provide the slides, we will be happy to share them too. And we look forward to the next lecture next week.
Thank you very much for having me.
Thank you. Then bye. And
thank you very much. See you next week. Bye.
Thank you very much. See you next week.
Thank you. Bye.
Yeah, that is full of thank yous. Federico, hello.
Great lecture.
Adiós a todo el mundo. Adiós, Rocío. Adiós.